Hello, welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communications. Alright. So, we are looking at MMSE estimation for a vector parameter, and as a particular example or as a particular instance of its application, we are considering the estimation of a downlink wireless of a downlink multi antenna wireless channel. That is, we are considering a base station which is multiple antennas, M antennas to be more specific, and a user who has a single antenna, and we are considering transmission from the base station to the user. That is, we are considering the downlink, and we have illustrated how to perform channel estimation for this downlink. Alright. So, the system model that we have considered is your y bar equals x h bar plus v bar. Okay. This y bar is your n cross 1 observation vector, x, this is the n cross m pilot matrix. Recall that your n equals number of observations, or basically number of pilot vectors, that is basically your number of and m equal to number of antennas. H bar is the m cross 1 channel vector, and V bar is the n cross 1 noise vector. H bar is naturally, it is an m cross 1 channel vector. It contains the m channel coefficients, one channel coefficient corresponding to each transmit antenna and the single receive antenna. Alright. So, for instance, if you consider the ith transmit antenna, the channel coefficient between the ith transmit antenna at the base station and the single antenna of the user, this is denoted by the coefficient Hi. Okay. So, H bar is this vector parameter, that is what we are talking about. H bar equal to, if you recall, this is basically H1, H2, Hm, this is your m dimensional vector. And therefore, we have a vector parameter. And further, we are considering a Bayesian vector parameter. Recall that we are considering a Bayesian vector parameter in which we are assuming each coefficient Hi to be Gaussian in nature with 0 mean and variance sigma h square. Alright. So, this is a Bayesian MMSE estimation scenario. Alright. So, there is some prior information about these channel coefficients or this channel vector to be estimated. Alright. So, we are considering H1, H2, Hm. To be more specific, we are considering H1, H2, Hm. These are IID Gaussian, which means basically independent identically distributed Gaussian with expected each Hi equal to 0, expected value, that is the mean of each coefficient Hi equal to 0, the variance expected magnitude Hi square equals sigma h square. Further, they are independent, which means your expected value of Hi into Hj, if they are complex, Hj conjugate equals 0 if I is not equal to j. Okay. Now currently we are considering only real symbols, alright. So I can simply call this as expected value of hi times hj, but if I have complex coefficients, and we can use this MMSE estimation framework also when the channel coefficients are complex, alright. I will shortly show you how to extend this to a complex vector parameter estimation scenario, and it is fairly simple. It is a relatively straightforward extension from the estimation of the real parameter to estimation of a complex parameter, alright. So expected value of hi times hj equals 0 if I is not equal to j and the parameters h1 or the coefficients h1, h2 up to hm are real parameters, alright. We are considering a real estimation scenario so far, and therefore the covariance, if you look at the covariance, we have expected value of h bar into h bar transpose, once again considering real parameters, that will be sigma h square times identity. Okay. And we also derived for this model that we have given over here, that is we have your y bar equals x h bar plus v bar. We have derived the various quantities. We have derived the covariance matrix of the observation vector y, that is r y y. This is the covariance of observation, and this we have said is sigma h square x transpose plus sigma square times identity. We have also derived the cross covariance or the cross covariance between r h y. This is nothing but expected value of h bar y bar transpose. This covariance matrix, this is nothing but expected value of y bar transpose. Okay. So this is expected value of y bar transpose, this is expected value of h bar y bar transpose, which we have derived as sigma h square times x transpose. Therefore the LMMSE estimate, remember, even when it is Gaussian, when the channel coefficients are non-Gaussian, we can talk about the LMMSE estimate. Of course, if they are Gaussian, then the LMMSE estimate itself is the MMSE estimate, that is the minimum mean square error estimate. Anyway, considering a general scenario, probably not necessarily Gaussian channel coefficients h, the LMMSE estimate is h hat equals, this is the estimate, that is r h y into r y y inverse into y bar, which is h hat equals, now I have to substitute r h h, this is sigma h square x transpose times sigma h square x transpose plus sigma square times identity inverse into y bar. Okay. So this is the expression for the LMMSE estimate. This is the expression for the LMMSE estimate. Now, of course, the LMMSE estimate itself is the MMSE estimate if the channel vector h bar is Gaussian, alright. Now what we are going to do is, let me simplify this LMMSE estimate in a form that is much more convenient, and I am going to illustrate that, okay. So now first realize, and again similar to what we have done several times before, realize I will start with this quantity sigma h square x transpose x transpose plus sigma square times identity, and I can expand this in two ways. I can take x transpose common on the left. So taking x transpose common on the left, that will give me x transpose sigma h square x transpose plus sigma square. I have changed this identity, this should be x transpose, okay, that will be sigma square times identity. Now I can also take, look at this, I can also take x transpose common on the right. So x transpose, taking it outside on the right, what am I going to have? I am going to have sigma h square x transpose x plus sigma square identity times x transpose, and naturally since both these quantities are derived from the same quantity, therefore I have these two quantities are equal since both are derived from the same quantities, which implies basically what I have, let me just write this clearly, I have sigma h square, let me just write it, sigma h square x transpose x plus sigma square identity into x transpose equals x transpose sigma h square x transpose plus sigma square identity. And now since both these quantities are equal, now I can multiply with this inverse of sigma h square x transpose x plus sigma square identity on the left. So this will come over here, this will become the inverse and come over here, and sigma h square x transpose sigma square identity, I can take its inverse and I can bring it on the right over here, and therefore now what you will observe, you can observe that what I have is, well, x transpose times sigma h square x transpose plus sigma square identity inverse, this is equal to sigma h square x transpose x plus sigma square identity inverse times x transpose, and this is the result that we have. Now I can multiply both sides with sigma h square, that is the last steps, multiply both sides with sigma h square, and that implies, that is very simple, of course sigma h square is a scalar, so I can simply multiply both sides by sigma h square. So I have sigma h square x transpose sigma h square x transpose plus sigma square identity inverse, this is equal to sigma h square x transpose x plus sigma square identity inverse times x transpose. And now if I look at this, now look at this quantity is sigma h square x transpose times sigma h square x transpose plus sigma square I inverse. Now if you look at this quantity, look at that quantity is exactly equal to this quantity. If I call this quantity as your star, this quantity is exactly equal to this quantity is exactly your star. So this quantity is equal to this quantity, which means I can replace this star by sigma h square x transpose x plus sigma square times identity inverse into x transpose, and therefore I will have h hat equals, previously it was sigma square h square x transpose sigma h square x transpose plus sigma square identity inverse into y bar. I can equivalently write this as, now replacing star by sigma h square x transpose x plus sigma square identity inverse times, of course I am missing a sigma h square here because I am multiplying both sides by sigma h square. So, times sigma h square is a scalar quantity. So, I can multiply it anywhere. So, sigma h square x transpose y bar. In fact, I can simply bring the sigma h square all the way to the left. I can write this sigma h square x transpose x plus sigma square identity inverse into x transpose y bar, that is your h hat, and this is the simplified expression. This is what we are saying as your simplified expression for the MMSE estimate. Or rather LMMSE estimate. This is the simplified expression for the LMMSE estimate. Okay. So, h hat equals sigma h square times sigma h square x transpose x plus sigma square identity inverse into x transpose y. Now, why we are saying this is a simplified estimate? Because look at this, if you look at the first expression, this expression x into x transpose, look at this. So, if you have x into x transpose, this is an n cross m, x is n cross m, x transpose is m cross n. As a result, this whole matrix will be n cross n. So, this x sigma h square x transpose plus sigma square identity is an n cross n. So, this is the inverse, we have to compute the inverse. In the first technique, we have to compute the inverse of an n cross n matrix. But if you look at this quantity x transpose is basically x transpose, this is basically m cross n, x is basically n cross m. So, this is basically your sigma h square x transpose x plus sigma square identity, this is an m cross m. In fact, if you look at this identity, the identity here is m cross m, the identity here is n cross n. So, in the first case you are inverting an n cross n matrix where n is the number of pilot vectors. Okay. In the second case, you are inverting an m cross m matrix where m is the number of antennas, and typically the number of pilot symbol vectors transmitted is always much more than the number of antennas. That is, if you look at n cross m, that is if you look at x, remember if you look at x is n cross m, n is number of pilots, m is antennas. Typically, number of pilots is much greater than the number of antennas. Number of pilots is much greater than the number of antennas, implies your n is typically much greater than m. Therefore, it is much easier to compute the inverse of an m cross, because n is much larger. So, n first matrix is n cross n, which means it is much larger matrix. So, it is much more difficult to invert. Alright, the second matrix is an m cross m matrix. Since m is much smaller, it is much more easier. It is easier to compute the inverse of this m cross m matrix rather than an n cross n matrix. So, the second one, that is the second implementation, has a much lower complexity. So, this one has a lower complexity. So, this one has a And in fact we had seen that earlier, we had seen a special case of this where m is equal to 1. When we have a single channel coefficient, then m cross m becomes simply 1. So the inverse is simply a scalar, correct. We might have n pilot symbols, that is 100 pilot symbols, but if m equal to 1, m cross m is simply 1 cross 1, which means it is a scalar quantity. So the inverse is of a scalar is simply the reciprocal, alright. And in fact that is the property that we had used earlier also to simplify the LMMSE or the MMSE estimate for a channel estimate, for the estimation of a fading channel coefficient with a single antenna, single transmit and single receive antenna. And now of course we are extending to the estimation of a channel vector corresponding to m antennas. What we are saying is we can do this with complexity of inversion of an m cross m matrix, where m is the number of antennas, rather than an n cross n matrix where n is the number of pilot symbols, alright. So let me again write that down, summarize that. The final channel estimate is h hat equals sigma h square times sigma h square x transpose x plus sigma square identity. This is m cross, this is an m cross m identity matrix inverse x transpose into y bar. Okay, so this is the LMMSE estimate. And now the additional thing that we can look at here is that for complex, I can simply replace the transpose by Hermitian. For complex channel vector, let me just write that down. For a complex channel vector, this is the trick that we use fairly often. You simply replace the transpose by the Hermitian, that is all you have to do. Sigma h square x Hermitian x plus sigma square identity inverse x bar Hermitian y bar. This is for a complex vector h bar. Remember we said in the beginning that this can be extended also to complex parameters, or when the channel vector h bar is complex in relatively straightforward fashion. The simple trick is to replace the transpose by the Hermitian. So it will become sigma h square times sigma h square into x Hermitian x plus sigma square identity inverse times x Hermitian y bar. That is a simple extension to the when the channel vector h bar is complex, that is the coefficients are complex, the transmitted pilot symbols are complex, the noise is complex, hence the received observations at the receiver are also complex. Alright, for the complex estimation scenario, this is the straightforward extension. Alright, and one small point to observe here, which is very interesting, that is, we look at this estimate h hat equals sigma h square x transpose, going again back to the real scenario, sigma x times x transpose y. Now consider the scenario where high signal to noise power ratio scenario. Consider a high SNR scenario. In high SNR scenario, remember what will we have? The signal power is much greater than the noise power. So look at this, this is a signal component, this is your noise covariance. In high signal to noise power ratio, the signal power or signal covariance is much stronger, much more stronger than the noise covariance. Therefore, what we will have is this sigma h square will be much larger, sigma h square x transpose x bar, x transpose x will be much larger than sigma square identity, which implies that I can neglect, that is sigma h square, which implies basically sigma h square x transpose x plus sigma square identity is approximately equal to sigma h square x transpose x. Okay, because the noise power or noise covariance is insignificant compared to signal covariance, I can approximate this quantity sigma h square x transpose x plus sigma square identity simply by sigma h square x transpose x. And now you can see something very interesting, therefore h will be approximately equal to, or h hat is approximately equal to sigma h square x transpose x inverse times x transpose y bar, which is equal to, now if I bring the sigma h square outside, this is a scalar quantity, this is equal to simply x transpose x inverse x transpose y bar, and this is simply, you can recall, this is the maximum likelihood estimator. This is the maximum likelihood estimator, and if you look at this quantity, in fact this is also known as the maximum likelihood, or this is known as the least squares estimator. Or the LS, least squares is basically short, it can be shortened as LS. And if you can look at this quantity x transpose x inverse x transpose, this is known as the pseudo inverse of the matrix X. Reason being, if you look at x transpose x inverse x transpose and multiply that by x, now you have x transpose x inverse into x transpose x, this is equal to identity. So, x transpose x inverse x transpose is pseudo inverse, or this is also equal to the left inverse of x, of pseudo inverse of matrix X, alright. So, x transpose x inverse x transpose is the pseudo inverse of x, it is also the left inverse of x, because if you multiply it on the left of x, you get the identity matrix, even though x might not be an invertible matrix, because n is greater than or equal to m, because remember, again this is very interesting, x is n cross m and n we are saying is greater than, can be greater than m, okay, n can be great, number of pilot symbol can be greater than the number of antennas. So, if n is equal to m, of course it is a square matrix and can be inverted, alright, if inverse exists, but if n is greater than m, then no inverse exists for x. Therefore, this matrix which when multiplied by on the left by x gives the identity, this is known as pseudo inverse, or basically this is acting as an inverse of x. This is a pseudo or a sort of a fictitious inverse of this matrix X. And what is interesting is at the high signal, in the high signal to noise power ratio, this MMSE estimator again reduces to the least squares estimator, that is the maximum likelihood estimator, alright. What is also interesting is what happens in low signal to noise power ratio. In low SNR, in this case the signal covariance will be very small compared to the noise covariance, that is sigma h square x transpose x is much smaller than sigma square times identity. Therefore, we have h hat, if you observe closely, h hat is sigma h square x transpose x plus sigma square identity inverse x transpose y. We are saying this is very small, this is much more smaller compared to sigma square identity, therefore, this can be approximated as sigma h square times sigma square identity inverse x transpose y bar. I have to write y bar over here, and what is this? Now, if you look at this, sigma square is a scalar, so this is simply sigma h square divided by sigma square times x transpose y bar. This is simply x transpose y bar, this is simply a matched filter. or your MF, because your signal is x, right. Your y bar equals x h bar plus v bar, you are simply multiplying by x transpose into y bar, and of course a scaling factor, right, sigma h square divided by sigma square. This is simply your matched filter, alright. So, it is very interesting. At high SNR it becomes the least squares estimator, the LMMSE estimator. At low SNR it becomes the matched filter, alright. So, that is a very interesting aspect, and the other interesting aspect of this is that this matrix sigma h square x transpose x means sigma square times identity, this inverse of this always exists even when x transpose x is not invertible, even when x transpose x is not invertible. So, this is also known as a regularized inverse, alright. So, this is known as a, and the sigma square identity is known as a regularization term. So, this is known as a So, what it says is if x transpose x is not invertible, that is you cannot compute the least squares estimate, what we can do is we can add a simple sigma square times identity term to that, compute the inverse of this. So, the inverse becomes stable. This is known as the regularized inverse, alright. So, this LMMSE estimate is beneficial because the inverse is always stable, even when x transpose x is ill behaved, it cannot be inverted. Sigma h square x transpose x plus sigma square times identity is always invertible, alright. So, the inverse is always stable. So, the LMMSE estimate is stable, alright, which means your solution can be computed in a very controlled fashion, right, without computing the inverse of, unlike least squares when x transpose x is not invertible, then the solution will become out of bounds, alright. It is similar to taking the inverse of 0, okay. So, the LMMSE estimate will always be a stable estimate because of the regularization nature of it, where you are adding sigma square identity to x transpose x and then taking the inverse. So, there are a lot of interesting interpretations of this LMMSE estimate, particularly for this vector scenario, alright. So, with this basically we have simplified the LMMSE estimate for the computation for the channel vector h bar, and we have also demonstrated several interesting simplifications, several interesting observations, what happens in the low SNR regime, what happens in the high SNR regime, etc. alright. And then subsequent module we will do a simple example to further illustrate this concept. Thank you very much.